Okay, welcome to the second video, and this time I'm going to do quiz 1. So in this tutorial I'm going to solve or give you some hints on quiz 1, which is it starts with this question here. This question where you have an electron and it's entering into a parallel plate capacitor where there is a uniform electric field. And what he wants you to do, he wants you to find the magnitude of the electric field. Actually, he gave you the magnitude of the electric field, and he gave you the separation between the plates and the length of the plates, or the area of each plate, and from which you can find that. He wants you to find the magnitude of the charge on each plate, and then he said that if the electron it has a charge together and mass together, what is the horizontal and the vertical component of the velocity of the electron after passing through the parallel plates? And then he is asking you how long did it take, or does the electron take to just clear the parallel plates. Okay, so let me just do this very quickly, because we've done similar example in class about this. Okay, so let's see what we have. We have a parallel plate capacitor, something like this. Okay, and if I recall, where is the positive plate is the if the electric field is this way, right? If the electric field is this way, that means this is positive, right? And the bottom plate is negative. Okay, and the electron enters here with some initial velocity v0x this way, projected somewhere half. So it's this distance here is actually 0.5 centimeter. Okay, so what we have to do, first of all, we have to realize that the electric field is defined as Q over epsilon A inside the parallel plate capacitor, which is a formula that we have derived in class. The electric field is uniform, the area is constant, Q is the charge on either plate, and epsilon naught in this case is the permittivity constant for free space, which is known. So to answer the first question, since he gave me the electric field, which is 6 kilonewtons per coulomb, then from here I can find Q is equal to the electric field, which is given, multiplied by epsilon naught multiplied by the area. Epsilon naught is given, the electric field is given in kilonewtons, so I have to multiply it by the area. He told me that the length of each side of the plate is 2 centimeters, and it's assuming it's a square. So that means it's equal to 0.02 square is the area. Okay, the plates each have length, not radius. So this is assuming that the plate is square. So, and I think I mentioned that in class during the. So anyway, so we found what the charge is. That's fine. It's just you plug in then A here, epsilon. You have everything. You can calculate that straightforward. That's part A of the question. Part B is he wants you to find the vertical and the horizontal component of the velocity as the electron leaves the the electron starts here somewhere, and then it went, of course, up according to and he wants you to find Vx and Vy at this point. What is that? As it clears, that means it's somewhere here, not there. Okay, as it clears, so that it means somewhere here. So that means the distance traveled along the y, delta y, is actually 0.005 meter, which is 0.5 centimeter. Yeah, so 0.5 centimeters. So delta y is equal to that. Okay, so we have to resort back to our kinematics equations, and we have to do a few things. First of all, we need the acceleration. Okay, what's the acceleration of the electron? The acceleration of the electron is defined as F divided by M. F is equal to ma, so F, and F is actually the electrostatic force that is exerted because of the field. which is simply equal to Q multiplied by E, the electric field, divided by the mass of the electron. And the electric field, already we have it. Q, we just calculated it. Sorry, no, this is Q of the electron. Q of the electron, and the electric field we not calculated, but it was given to us, and M of the electron is given. So this is a number now. We have it in meter per second square. Once I found that, the next thing that I wanted to do, I wanted to find the time taken, because I have delta y. So I can use the equation which says that delta y is equal to v0y t plus a half a t squared. Okay. Now the acceleration is upwards, so I don't have to worry about the minus sign. Delta y in this case again is upwards, which is equal to 0.005 meter. v0y, the electron was projected horizontally at the initial velocity. It's only v0x, so v0y is 0. This goes, and then it's equal to a half multiplied by a. A is this value here, and then I can find t from here. So t will be the square root of 2 multiplied by this divided by a. I got the time. Okay, which I answered. Actually, I answered question C. This is part C. To calculate part C, t is actually 2 multiplied by 0.05 divided by the acceleration, which we found it from here. So I found that in seconds. All right. So so that's the time. Once I found the time, then it should be easy for me to go back. It should be easy for me to go back and find the components of the velocity. Vx will not change. It's equal to v0x, which is the value that is given for us. It's equal to 3 times 10 to the power of 6 meter per second. Because, why is this true? Because there is no acceleration along the x-axis. There is only acceleration along the y-axis. For vy, I can find it from v0y plus a t. I know a and I know t, so I can find vy and problem solve. Both a and t are from the first part. Okay, so that's the solution to the first problem. Now the second problem, this is the one that some people had difficulty with. The second problem, which, let me just use a piece of paper here. Okay, so the second problem here, it says that, let me just read it with you. Okay, it says that a small spherical insulator of mass equal to 60 grams, and it has a charge 0.4 positive microcoulombs, is hung by a thin wire of negligible mass, so the wire does not have any effect here. And then a second charge, which is negative 0.2 microcoulombs, is held about 30 centimeters away from the mass. If the system is at equilibrium, find the angle and the theta, okay, with the vertical, so that he wants you to use equilibrium conditions. Some of the forces equal to 0, some of the forces along y is equal to 0, to find the value of the angle theta. Okay, so this is really a physics 1 problem. It's not a physics 2 problem, but it has some applications of what we've done in class. Okay, so what do I have here? I have this mass, okay, and it has a mass and a charge. And if this is theta, when I do my analysis, this will be also theta. Okay, and there is this is positive. This is positive, and then there is another charge here located, which is negative. Now immediately I know there will be a force for this guy. There will be an attractive force this way, an attractive Coulomb force this way, Fc, and that Fc is equal to K Q1, Q2 divided by the distance between them square, which is simply K. Q1 is equal to, 0.4, and the other one is minus. So this will be negative, and it means it's on the other side. It's going this way. So Q1, Q2, the magnitude of it, let me just say the magnitude of it, divided by the distance, which is 0.3 square. So I got, let me call this Fc. So Fc is that direction, and I know its magnitude, and I know it's that its magnitude, and I know the direction is towards the negative. Now, in order for this to be balanced, there must be another force pulling on it this way, or affecting it this way, which is, it should be the same magnitude as this guy. Okay, that's what the balancing condition is. How do I get that? Well, I notice that there is tension here. Okay, tension is always away or out of the mass, and this can be analyzed to two components. T, let's call it T vertical. T vertical is equal to T cosine theta, right? This is the angle theta. Okay? And this component will be T sine the angle theta, and of course I have mg down. Okay, and this is my free body diagram. If I get a fresh sheet paper, and then I can now, the next step is to write my the sum of the forces along the vertical dy is equal to actually, let me start with the sum of the forces along x, just so that, because I want the sum of the forces along x is equal to fc, which I've calculated, minus t sine theta is equal to 0. And the sum of the forces along y is equal to t cosine theta minus mg is equal to 0. Okay, I have two equations. I need theta, that's what he asked me for. So if I rearrange these equations, equation number 1, I can write it T sine theta is equal to Fc, and equation number 2, I can write it T cosine theta is equal to Mg. So I notice that if I divide these two guys, T sine theta over T cosine theta is equal to Fc divided by Mg. As you can see, I have tangent theta is equal to Fc divided by Mg, and that's my solution. I have Fc, which I calculated in the previous slide, and I have the mass and I have the G. The only thing that I have to be careful with is the units. Remember, you have a microcoulomb, you have a milligram, and all of these things, you have to convert them into the proper units so that they are all consistent, all in MKS, so meter kilogram per second. Okay, so that's the second problem. Okay, the third problem is this one, which I discussed in class, to be honest with you, and we solved it in class, and I was a little bit surprised that some people did not pick it up. But what do we have here? We have charges placed on a square, or the corners of a square. Two of them on the top are q, and the bottom one is 2q. And he wants to know, just using vectors, he wants to know the direction of the electric field, the resulting electric field. Okay, let's see how we're going to do that. Okay, so let me start here. I have a q here, and I have q here, and I have the advantage of the square. That means all these distances are the same. Okay, so to get the electric field, I'm going to place a positive test charge here in somewhere. So I'm going to place a test charge q naught, which is positive, somewhere here. So this is all of these guys are positive. So that means if I use vectors to indicate, so this, if I take the, let me call this one, so I have a vector here, okay, let me call this q1, so this will be F, or the electric field due to 1. And same thing, this I'm going to call this 2, so then I have another one which is 2, E2. And I have a third one which is now twice, so if this is 1, and this is another 2. Okay, so if this is E1, this is E2, this is E3, these guys are the same, but this guy is twice that because I have TQ. Remember, the distances are the same. So let me resolve these vectors. Okay, so the magnitude of this guy is twice as these two. If I resolve this, okay, I get, okay, so this one, I get vector like this from this guy, and I'm going to get a vector like this from this guy. Okay, that's this guy is gone, and then I'm going to get another one, okay, from this guy, and another one from this guy, another vector, and this is gone. So I immediately see that now I have these guys cancel. But wait, I have this guy is going to give me 2 on this side. okay, and it's going to give me 2 on this side, okay. So what does this mean? This means that these two together will cancel this, so that means definitely the EY is equal to 0. EY is equal to 0. And for the EX, this guy will cancel with this one, and I still have 2 of this. So the direction of the direction of the resultant will be this way, and it's equal to he just wants the direction, so that will be the direction of your result. Hopefully you saw how I did that. Okay. If you have any questions, yeah, you can ask me during class or during the office hour anytime. But you saw how I did that. Okay, so this is positive charge. You have 1 this way. Positive and positive will repel each other, and positive and positive will repel each other, and so forth. Okay. Question number 4 is this question here, where it says that you have a dipole, an electric dipole. And what about this electric dipole? He gave you the charges, and he gave you the separation between the dipole, the charges, and the electric field. He gave you the electric field. If theta was equal to 120, what's the net torque on the dipole? Okay. And second, he wants you to find the total energy. Okay. Let me just, because this is a very straightforward question, should not give you any problem. I'm sure you guys did not have any problem with it. So this is my dipole, okay, and the electric field is this way, and the angle between them, he said it's 12 degrees. So the angle between them is 12 degrees, not 120. And this is the positive one, positive charge, and this is the negative charge. Now the force, as we showed in class, this will be my positive force, and this will be my negative force. Okay, so this negative. So the rotation of the dipole, it will be this way, right? It will be clockwise. Okay, that's the rotation of them. And he gave me the distance between these two guys. The separation is 1.2. L is equal to 1.2 millimeters. So that means I have to convert it to meters. First of all, he wants the net torque. The net torque will be equal to torque positive plus torque negative. Okay, it will be FR sine theta plus FR sine theta. We saw that it's equal to 2 FR sine theta. So 2 FR sine the angle theta. Okay. All right, because this is 12, this is 12, so you have the same thing there, right? So from here you can find the net torque that is rotating or creating the rotation. All right, find the energy, find the total energy when the dipole completes 1 revolution. Now, if you recall, when we calculated the potential energy U, we had we had the P and then E D what is that? No, actually torque. Sorry, torque d theta. Okay, and remember the torque is equal to PE, because this is QE, and this is R, which is A, so this is P. This leads to P is equal to Q multiplied by R, and then you have E, so it's Q PE sine theta. The dot product. Now, if you do that, this is energy, so it has to be dot product. Yeah. So when you do that, it's the torque multiplied by cosine theta d theta. Okay, cosine theta d theta. And I think I made a mistake. Actually, no. The energy will be equal to no, that's fine. That's PE cosine theta. Now the only thing that you need to know here is that you're going from theta 0 to theta final. Now when you're doing a complete revolution, so you're starting here and then you go all the way back. So you're going from 0 to 0, which means what?